Okay, I'm going to do. Where is P? Yeah, FP plus 12, right? Because old frame pointer, old program counter, first argument. So if I want to return star P, what do? I load P, FP plus 12, into R0, and now I load R0, right? There's the indirection step, into R0, and then I go ahead and return it. It's already in R0, okay? And then in main, what do? We push 8 for the arguments. We put 15 into J, so move 15, put it into R0, store R0, put it into J, which is at FP. Okay, and then when I call A sub J, now I've got to push the address of J onto the stack. So it's already there in the frame pointer. So that's into SP minus minus. And now I can call JSRA, pop 4, and then set store the return value, which is in R0, into I, which is in FP minus 4. Okay. So, all fairly straightforward. The only part of that that's confusing well, there are two parts of this that are a little confusing. One is that you're doing this 2 levels of indirection, one to grab the pointer and then one to dereference the pointer. And then here, we're putting that pointer value onto the stack. Okay. Let's do a harder one, I think. Yeah. Okay. Push 4. Okay, with arrays are just like pointers. The only difference with a array is now you've got to take whatever the index is of the array, multiply it by the size of the array, by the size of the element, add that to the pointer, and then dereference. Okay. Now, the compiler is typically smart enough to know that if it can skip some steps, it will. So for example, here, if I say I equals P0, the compiler is going to know that it doesn't have to multiply 0 by 4 and then add it to the pointer, right? So it'll just do all of that while it's doing the compilation. So this is the same thing as doing star P. So you would say load FP plus 12 into R0, then load R0, R0 into R0, and then store that to I. So store R0 into I. Where's I? I know you're not paying attention. Anyone, where's I? There we go. I's at the FP. The more you pay attention, the less likely I'm to want to ask questions about this in a more formal setting. Just saying. So I know it's dry, but it helps you understand pointers. It just helps me understand pointers. All right, here, we're going to do X P3. Now, again, the compiler isn't going to have to say, hey, let's load 3 and load 4 and multiply them. It makes no sense. The compiler is going to know that we want to look 12 bytes past past P. So the compiler will go ahead and move 12 into R0 and then add then load FP plus 12 into R1, and then it'll add them. R0 and R1, put the result into R0, okay? That gives me what's there, and now I need to go ahead and do the indirection, R0, and then store R0 into FP. Okay? And now the last one, the compiler does have to do more work now, right? Because the compiler is going to have to load I, load 4, multiply them, load P, add that product to P, and then dereference. Okay? I might even have a picture of that. Let me see if I got a picture. Yeah, I do. I have a picture. It's not that exciting, but yeah. So, this is what you're doing, okay? We got a load I, multiply it by 4, load P, multiply them, that gives you the address of P of I, and then you do the dereference, and that gives you P of I. Okay. And can we do it, and the nice thing is with this shape, we can do it all in 2 registers. So we don't need to do any spilling. All right, so here we can, let's go ahead and do it. All right. Move 4 into R0, load FP into R1, multiply them. Result in R0. Now I go ahead and load P. That's going to be FP plus 12 into R1, add them. And then once I've got that done, so that's actually the value I want, now I got to dereference it. So load R0, put that into R0, store it into I, store R0 into I, and we're done. Okay? Now, 20 minutes, I swear it'll go like 5. Let's look at this code. Because this code's simple, but it's still kind of a pain. Okay? So, if you see any bugs, let me know, because we're going to run this one. All right, what's the first command that I'm doing here? Push what? Push 20. That's exactly right. 20. Now, arrays are weird because there's no 4-byte value for array, right? We just know where the compiler knows where array is. It's the first byte. So what is it? In reality, it's FP minus 16, right? I called push 20. That went and added 20, and now we've got array 4 is going to be at the frame pointer. Array 3 is at frame pointer minus 2, minus 8, minus 12, minus 16. If I said plus before, I'm sorry. It's minus. So, what do? We can say move 10 into R0s and store R0 into FP minus 12. So that's the nice thing, is you can do arithmetic with the frame pointer while you're doing that operation. That's the legal hardware operation, because it's something you do a lot. So now doing these is real simple, right? So 1, 2, 3, 4, right? We can do 11, 12, 2, 15, right? And then that's going to be, no, that should be 16, 12, 8, 4, 0. Okay. Now, when I call A, what do I have to call it on? I've got to call it on the value FP minus 16, right? Because that's the address of the first byte of array, right? So what I've got to do arithmetic. So I'm going to have to say move 16 into R0, add R0 and FP, put the result into R0, store R0 onto the stack, right? So this is how the compiler, this is how this weird magic of arrays goes, right? Because with arrays, there's no variable for an array, but when you use it, it will use the pointer to the first byte. That's how this is working, right? It's finding the pointer to the first byte, pushing that on the stack, and now I can treat it like a int star. So now I'll call JSR A, pop 4, and then I do nothing. Return. Okay, so if I'm running this code, what should the values of I be? Right? In the first one, what's the value of I going to be? 10, right? You didn't need to know any assembly code for that. It's 10. Second one, it's going to be And the third one, it's going to be 12. Right. So when we test it, we want to make sure it is those things. We're going to be setting I to 10, 12, and then 2. Okay, so no, that's not going to work. Think it's going to open? Ooh, that's a good day. All right, so here, let's scroll our code. So allocate the array, right? So that just gave me my 20 bytes. And now we're going to successively, we're going to put the value 10 into here. Here's array 0. Sorry, this is hard to read. Okay, but that says 0x0a because that put 10 there, right? And so now we'll put 11. There's 11, 12, 2, 15. Okay. Now what are we going to do? We're going to put -16. Ooh, this code's got a bug. That should have been -16. Or that should have been subtract. Let's fix our bug.
Do you need ret at the end of A?
Can I do what now? I'm sorry?
Do you need ret at the end of A?
Oh, I do. What happens if I don't? It just spills into main. Thank you, Team Plank. We'll do it again. Okay, scroll the code down, and there. There we go. 2 is in there, 15's in there. Okay, now we go ahead and we put -16 into register R0, add that to the frame pointer. The result of that should be FFF438. Boom, FFF438. Then we go ahead and push that on the stack. Okay. Now we call JSRA, which is there. Let's go to where our code is. Okay. Now it's going to do those 3 things, right? The first one is it's going to dereference FP plus 12. So it'll dereference this and store it into I. So I's value should be A. And here's where I is going to be. I haven't done the push yet. So push. There we go. Load the value into R0, store R0 into I. There it is. All right, so I is that. The next one is going to load the value. Well, so it's going to load the value and then add 12 to it. So here it loads 12, loads P, the pointer, adds them. That gets 444, which is what we thought it should be right here. Dereferences it and loads it, stores it into I. Okay? And then the last one is going to put 4 into R0. It's going to put I, which is at the frame pointer, which will be 2, into R1, multiply them, which gets you 8. Get the value of P, add 8 to it, dereference, that's 12, store it, it's 12. Okay? So that's how those array things work. All right, this is a fine stopping point. The next one, we'll stop after the next one. This one's kind of rough. All right, what this program has is a bug. It's got a big old bug in it. This is the kind of bug you could have. The compiler might find this one for you. I would think most compilers probably won't find this bug for you. Okay, the bug's in B. Okay, so look at what B is doing. B allocates an integer array, and then it returns the ith element to it. Well, we haven't ever initialized it, right? So we've got uninitialized memory that we're returning. But because we know JASM, this is deterministic. I mean, actually, this program, it is deterministic what the answer is going to be. It's a buggy program, but we could calculate. And if I were a dick, I could ask you on an exam, right? Give me the output of this program. Take you 25 minutes to give me one single value, which may or may not be right. You'd probably be better just to roll the dice and move on. Okay. But we can do it, so let's do it. We've got 12 minutes. Yes, sir.
Doesn't A need a function type?
Oh, it does. Old school C. Look at that. I'm never fixing that in the lecture. If I remember, I'll fix that in the lecture notes. In the old days, procedures defaulted to int. And used to do this. That's old school C right there. That's how C used to be. It's awful, isn't it? I mean, it's so much better the way it is. I'm never much one for change, but that's a good one. That was a good change. All right, let's go ahead and write the code. This is all fairly straightforward code, right? This one's really straightforward code, right? I'm gonna load I. Where's I? Where's I? Please, someone tell me where I is and be correct. Please. FP plus 12. All right, so load FP plus 12 into R0. Where's J? That's 16. Yeah, now we got that. The ice has been broken. All right, add R0, R1, put the result back in R0. Here, let's do that 2 more times. All right, that's going to be 20. That's going to be 24. And then store the result into M. So we can say store R0 into M. Where's M? FP, good. Return. All right, that was a nice easy one. Let's do main. Main's easy too. All right, push 4. And then move. What value am I going to move into register? Oh, I just wrote it in there with muscle memory. There, you all got hundreds. Okay, store R0 onto the stack. All right, and now I think you all can figure out the rest. All right, 7, 6, 5. Remember, you push them in reverse order. JSR A, pop 16. The return value, we don't care about the return value. Now we're going to push 2 onto the stack, or we need the value 2 on the stack. So move 2 into R0, store R0 onto SP minus minus. JSR B, pop 4. And now we're going to take the return value and store it to X. So store R0, put it into the FP. Return, we're done. All right, those are the easy ones. Now this one is more of a pain. Okay, so B. What's the first instruction here? Yep, push 20. And now we need to return P of I. Well, we kind of did that before. What do we have to do? We need to load I. So load I is going to be at FP plus 12 into R0. We're going to load P. Right? Where's P? Oh, yuck. P's at FP minus 12. I'm sorry, minus 16. Right? And we got to calculate it. That sucks. Okay. Let me, before we do that, oh, we got a lot of pointer. Yeah. Here's our tree for calculating P of I, okay? So we take I and 4, multiply them. Now we got to find P. So to find P, what we're going to do is we've got to subtract 16 from the frame pointer. Right? We don't have that enter stored anywhere, so we've got to calculate it. Once I do that, now I can add those two, and that gives me ampersand of P of I, and then I go ahead and dereference. Okay? Now here's a pro tip. Since addition is commutative, was this commutativity or associativity? Not quite sure. I think this one's associative. I can turn this tree, which is kind of bushy, into one that's longer, right? It doesn't matter, that's commutative. It doesn't matter what order I perform these additions in, right? So I can turn this tree into a different tree, that one. And that's nice because now I don't need to spill R2 to do this calculation, right? I can do load, load, multiply, move, add. Don't even do anything, add, and we're good. So let's go ahead and do it. This picture makes life very nice for us. All right, so here we go. We will, I already did that. Let's go ahead and move 4 into R1, multiply them, R0, R1, roll into R0. Now let's go ahead and move negative 16 into R1, add them, result in 0. Now I can just add the frame pointer, and now I dereference. What am I doing? Am I returning it? I'm returning it. So I can say load R0 into R0, and I'm done. Yes, sir.
Can you remove negative 16?
Thank you, Team Plank. Anything else? Uh-oh. Do I know return? Thank you. Oh, I can change it before I load it. There we go. Thank you. I miss a return there too? No. Ooh, it is a good day. Okay, so what's this code do? So the first code that's being run is it's going to push 8, 7, 6, and 5 onto the stack. Let's go ahead and step to that, all right? So 8, 7, 6, 5 onto the stack. Now it calls JSR. Boom. Okay. What does A do? I forgot what A does. What does A do? Oh, it just adds them, right? Where am I? Here. Okay. A is going to add them. So it's going to 5, 4, 3. Here we go. 12 plus 8 is 1XA. That gets stored here. Okay. On the stack, and then it just returns, no return value. Okay. Then in the code, then what do? We call B. Did we give B an argument? Hello. Okay, we gave B, so now we're going to call B with an argument of 2. Call B, and then we're going to go find that argument on P. So back to JASM. Okay, we're going to put 2. We're going to put 2. Well, we first got to pop. Boom, pop. Now we're going to push 2 on the stack. Okay, then we call JSRA, which is there. Now, first thing that A does, it's up here. It's called push 20 to allocate that array. Okay, so there it is. So now what you can see is this array that we haven't initialized. Some of its this value, in fact, is not deterministic. I gave it 0 because I just always give it 0. But that value we've never touched. But you see there, this was I in the procedure A. There's my old. When I called A, here's my old frame pointer. Here's my old program counter. Here's my old argument, right? So those are what's sitting there in that array. So when I go ahead and grab value 2, right, it's going to be right here, 448. That's what's going to get returned from my procedure. So let's do it. Okay, we do that. Let's multiply R. That gives us the 8. Okay, go ahead and there is adding 16. There's the pointer. Here it is. There's the pointer to piece of I, which is sitting right there. And now when I dereference it, I'm going to get 448. All right, that's what gets stored. And so when I'm done, that's going to be the end. That's going to be my value. So again, that'd be a cruel question to ask on an exam. I'm not asking assembler questions, but if I asked a question like that, you should be able to do it and give me a precise answer, even though you have buggy code. Now, this code's going to change from compiler to compiler to machine, right? Everything runs a little differently, but at least it's deterministic. Okay, questions. I know this has been a bit of a slog, okay, but I do think it's really important information. Any questions on this? You're ready to work on your next lab. Are you working on TARCs? TARC. Oh, you're doing TARC, and then you do TARCs. Spend time early. Give yourself enough time to do these labs. Okay. All right. See you Thursday.